Uranus is cooling right now, and that was not supposed to be the story. A world this active in its upper sky should not be quietly losing heat like this, unless the glow above the planet is hiding a very different kind of machine than we thought. So the real question is simple. What did NASA's new map actually prove about Uranus, and what is it still refusing to explain? For years, Uranus looked like the kind of planet people forgot about. A pale blue ball, far away, quiet, cold, almost blank from a distance. But when you start pulling at the details, that calm picture falls apart very fast. If you want the full picture before the easy version spreads everywhere, stay with this story. Subscribe and stick close because this is one of those space mysteries that only gets stranger when the data gets better. At first glance, Uranus should have been simple. It is the seventh planet from the Sun, about 2.9 billion kilometers away on average, so sunlight out there is weak. It is huge, about 4 times wider than Earth, but it also looks smooth and calm compared with stormy Jupiter or banded Saturn. That made a lot of people treat it like the quiet one of the giant planets. But Uranus was never really quiet. It spins tipped over on its side, with an axial tilt of about 98 degrees, which means it almost rolls around the Sun. A year there lasts 84 Earth years, so each season can stretch for about 21 years. That alone tells you this planet does not live by normal rules. Then there is the problem of how little we have actually seen up close. Only one spacecraft has ever flown past Uranus, and that was Voyager 2 in January of 1986. It gave us the only close look we have ever had, and then it kept going into the dark. Everything since then has been built from distant telescope views and careful guesses. Voyager 2 did not come back with a neat, easy answer. It found a magnetic field that looked badly misaligned with the planet itself. NASA says that magnetic field is tilted by nearly 60 degrees from the spin axis, and it is also offset from the planet's center. In plain words, the invisible field around Uranus is crooked, lopsided, and weird. That matters because magnetic fields shape auroras. On Earth, auroras happen when charged particles slam into the upper atmosphere and make it glow. At Uranus, the same basic thing can happen, but the field lines guiding those particles are not neat and stable. They swing around a planet that is already tilted in a way no other major planet is. Now add one more layer to the puzzle. The part scientists wanted to map is called the ionosphere, which is a high region where gas gets electrically charged. It sits far above the cloud tops, in the upper atmosphere, where the air is thin and strange things happen. That is where the planet's magnetic field and atmosphere really start talking to each other. And this is where the old mystery had already begun. For decades, scientists had signs that Uranus's upper atmosphere was hotter than sunlight alone should make it. That is a known problem on giant planets because some extra energy source seems to help heat the upper air. But Uranus then added a twist by seeming to cool over time instead of staying steady. That trend started showing up in the early 1990s. Year after year, later measurements suggested the upper atmosphere was not holding the same level of heat. The planet was still distant, still tilted, still magnetic, still capable of auroras, and yet the upper air seemed to be losing energy. That was hard to fit into a clean model. Here's what made the problem even worse. Old measurements could tell us broad things, but they did not really show the vertical structure of the upper atmosphere. Scientists could estimate temperatures, watch glowing signals, and compare years, but they could not fully see how conditions changed with height. It was like trying to understand a whole weather system from one thin strip of light. So the planet kept its secret for a long time. Was the cooling real, or just a trick caused by bad timing and limited views? Was the magnetic field dumping energy into some places and starving other places? Or was Uranus doing something more basic and more shocking, something that would force a rewrite of how ice giants work? Before the next piece lands, make your call. Did Webb find a hotter upper sky, a colder one, or a strange mix that broke both ideas? Drop your guess in the comments before we move on. On January 19, 2025, the James Webb Space Telescope turned toward Uranus for about 15 hours. That is close to a full Uranian rotation, since a day there lasts about 17 hours. The observation came through Webb's NIRSpec instrument using a tool called an integral field unit. That means Webb was not just taking a pretty picture, it was building a map from light. The team behind the work was led by Paola Taranti of Northumbria University under Webb Program 5073 led by Henrik Malin. What they wanted was the faint glow from high above the clouds. More exactly, they were looking at signals from charged molecules in the ionosphere. Those tiny signals can reveal temperature, density, and where energy is flowing. One of the key clues came from something called H3+. That is a charged form of hydrogen that glows in infrared light, which is the kind of light Webb sees very well. You do not have to remember the name, just remember this. When that glow changes, it tells scientists what the upper atmosphere is doing. Now watch what happens when the picture turns vertical. For the first time, scientists were able to map the upper atmosphere of Uranus in 3 dimensions. Not just across the planet, but upward through the sky, all the way to about 5,000 kilometers above the cloud tops. That is the first real vertical view of Uranus's ionosphere ever made. And the structure was not flat or simple. The temperature did not rise evenly, and the charged particles did not sit in one smooth layer. Instead, the new map showed that temperature peaks between about 3,000 and 4,000 kilometers above the cloud tops. That means the hottest part of the upper sky was not where many people might have guessed. The density of the ions told a different story. Those charged particles reached their strongest levels much lower down, around 1,000 kilometers above the clouds. So the place with the most charged material was not the same as the place with the highest temperature. Right there, the planet was already breaking any simple idea that one thing was controlling everything. That split matters more than it sounds. If temperature peaks high up while ion density peaks lower down, then energy is moving through the atmosphere in a layered way. Some process is heating one region, while the charged material stacks up more strongly somewhere else. Uranus was not acting like a smooth, evenly stirred globe. It was acting like a system with hidden channels. Then came the number that changed the tone of the whole story. The team measured an average upper atmosphere temperature of about 426 kelvins. That is about 150 degrees Celsius, which sounds hot, and it is hot by human standards. But for this layer of Uranus, the shock was not that it was hot. The shock was that it was cooler than earlier measurements had suggested. That point is easy to miss, so hold on to it. Uranus is a freezing world overall, but upper atmospheres on giant planets can still run much hotter than the clouds below, so nobody was expecting ice at the top. What stands out is that this upper region seems to be less hot than it used to be. And that is where the unexpected part becomes real. Webb did not just take a nice new look. It confirmed that the cooling trend seems to be continuing. The new data fit a pattern that appears to stretch back more than 30 years, to the early 1990s. In other words, Uranus may truly be losing heat in its upper atmosphere over decades. That is not a small correction. It means the old puzzle survived the arrival of better tools. A weaker telescope might leave room for doubt, but Webb is not guessing in the dark. It is one of the most powerful space observatories ever built, and it just backed up the cooling trend instead of making it disappear. So now the mystery gets sharper. If auroras and magnetic activity are feeding energy into Uranus's upper atmosphere, why is the average temperature still trending lower? Why are we seeing signs of action and structure, yet also signs of long-term cooling? Those two facts do not sit together easily. Pause here and lock in your next prediction. If Uranus was glowing with auroras, would the map show one bright region, a ring, or something stranger split across the planet? Put your best guess in the comments before the reveal. Webb found not one simple auroral patch, but 2 bright auroral bands near Uranus's magnetic poles. That alone told scientists the magnetic field was carving strong patterns into the upper atmosphere. The glow was not random, and it was not spread evenly. It was being guided into certain regions by invisible geometry. But even that was not the strangest part. Between parts of those bright bands, the team saw a distinct drop in emission and ion density. A dimmer zone sat there like a missing piece. Instead of a clean, glowing arc, the map showed a kind of broken structure. That darkened region matters because it hints at how the field lines are arranged. Charged particles travel along magnetic field lines, so if the geometry changes, the energy path changes too. A gap in glow can mean fewer particles are reaching that spot, or they are reaching it in a different way. The atmosphere was not just glowing, it was tracing the hidden shape of Uranus's magnetic field. And this is where the old Voyager 2 result comes roaring back. Uranus does not have a tidy magnetic field centered inside the planet like a neat bar magnet. Its field is tilted and offset, which means the auroras can sweep across the world in strange ways as the planet turns. Over a 17-hour day, the upper atmosphere can move through changing magnetic conditions fast. So think about what that means from the ground level of the puzzle. A planet already spinning on its side is also dragging around a lopsided magnetic cage. That cage funnels charged particles into the upper atmosphere, but not in stable, Earth-like patterns. What Webb saw was not just a glow, it was the motion of a warped system written into the sky. Scientists had reason to expect some auroral heating. At Jupiter and Saturn, auroras can help pump serious energy into the upper atmosphere. That is one reason giant planet thermospheres, the hot upper layers, can stay hotter than sunlight alone should allow. So a natural guess for Uranus would be this: active auroras should help keep things warm. But the Webb map complicated that idea right away. Yes, the auroras are there. Yes, the magnetic field is leaving strong marks. Yet the overall average temperature still supports a long cooling trend, and the heating does not look like a simple polar blast spreading everywhere. The engine is running, but not in the way many people expected. Now, the earlier picture of Uranus starts to break apart from both sides. It is not a dead, dull ball with nothing happening above its clouds. And it is also not a simple aurora-heated machine that solves all its own temperature problems. It is active, but the activity is uneven, layered, and somehow not stopping the long drift downward. Here's another reason that matters. Uranus takes 84 Earth years to go around the Sun, and because it is tipped over so far, its seasons are extreme and long. One part of the planet can spend years getting very different sunlight from another part. So scientists have to ask whether some of the temperature change is tied to season, not just to magnetic physics. But even that may not be enough. Sunlight is weak that far from the Sun, and the upper atmosphere is shaped by more than just daylight. Waves moving up from deeper layers may carry energy. Charged particles from space may add energy. The magnetic field may steer that energy into some places and away from others. What Webb has done is narrow the room for vague answers. Before this, it was easy to say Uranus was probably doing several things at once. Now there is a real vertical map, real temperature structure, real ion density structure, and real auroral geometry. That means every future idea has to face a tougher question. Does it match the pattern or not? Before we go further, make one more call. Do you think the long cooling is mostly driven by sunlight and seasons, or by something inside the planet's own energy system? Leave your pick in the comments because this next step changes the balance. The simplest answer would be to blame the sun. Maybe Uranus just receives different sunlight through its giant long seasons, and maybe that slowly changes the upper atmosphere. That sounds clean, but the new map says the story is not clean at all. The magnetic field is shaping where the action happens, and the temperature pattern does not look like plain sunlight painting a globe. So now the case splits in two. Part of the story may indeed be seasonal because Uranus is one of the most season-twisted planets in the solar system. But another part clearly depends on how magnetic structure and charged particles move energy through the upper sky. The unexpected result is not one weird number. It is the way several weird facts refuse to line up. And there is an even deeper problem hiding under all of this. For years, planetary scientists have dealt with what is often called the giant planet upper atmosphere problem. In simple terms, the upper layers of these giant worlds are usually hotter than sunlight alone should make them. You need extra heating from somewhere. Uranus should fit into that larger puzzle, but not like this. Its upper atmosphere is still much hotter than simple sunlight math would suggest. Yet the new average of about 426 kelvins is lower than earlier spacecraft or ground-based estimates. So Uranus is still too hot by one rule and getting cooler by another. That is a hard combination to explain. One possible idea involves waves. Deep below the ionosphere, the atmosphere of Uranus can move, shift, and create waves that travel upward. As those waves rise into thinner air, they can break and dump energy, somewhat like ocean waves crashing on a shore. That could help heat certain layers more than others. Another possible idea involves charged particles arriving along magnetic field lines. If those particles strike the upper atmosphere in changing patterns, they can create both auroras and local heating. But the Webb data suggests that whatever heating is happening is not simply spreading out and lifting the whole region evenly. Some places glow brighter, some grow dimmer, and some heights heat more than others. Then there is the dark gap between the auroral bands. That feature may sound small, but it is one of the strongest clues in the whole map. It suggests a boundary or transition in the magnetic setup, a place where field lines guide particles in a different way. That is the kind of detail scientists wait years to see because it turns a blur into a structure. A similar kind of darkened region has been seen at Jupiter. That comparison matters because it tells scientists this may not be random noise in the Uranus data. It may be a real fingerprint of how magnetic geometry controls particle flow. The difference is that Uranus is doing it inside a much stranger magnetic arrangement. So the picture gets more serious now. The new map does not just say Uranus has auroras, it says Uranus has auroras shaped by a tilted, off-center magnetic field that leaves clear marks in temperature and ion density. That means the atmosphere and magnetosphere are tightly linked, and they are linked in a way we can finally trace. This is also why one observation can matter so much. Webb watched Uranus for nearly a full rotation in one long run. That gave scientists a way to compare different longitudes, which means different slices around the planet, as conditions changed. Instead of one snapshot, they got something closer to a moving scan of a live system. Now comes the part where people often rush too fast. A better map is not the same thing as a solved mystery. Webb has shown the structure, confirmed the cooling trend, and revealed how odd the auroras really are, but it has not yet told us exactly why the cooling continues, or how the planet balances its energy over time. So here's the question I want you to answer before the next turn. After all this, does Uranus sound more like a dying world losing power, or a living system moving power in ways we still do not understand? Drop that choice in the comments before we push toward a verdict. The stronger answer is the second one. Uranus does not look dead in these data. Dead worlds do not usually show this kind of layered structure, bright auroral bands, magnetic shaping, and changing energy paths. What Uranus looks like is misunderstood. That may sound like a softer conclusion, but it is actually bigger. A dead planet is simple. You stop asking hard questions. A misunderstood planet is dangerous to old ideas because every new measurement can break a model people trusted for years. That is exactly what Webb has done here. And the target of that damage is the old idea that distance means stillness. Yes, Uranus is far away. Yes, it gets much less sunlight than Earth. But far away does not mean inactive, and cold overall does not mean simple overhead. Its upper atmosphere is alive with structure. The other damaged idea is just as important. We can no longer talk about Uranus's upper atmosphere as one smooth, hot shell floating over the planet. There are heights, layers, bright zones, dim zones, and strong changes from place to place. This is not a flat blanket. It is a shaped system with routes, traps, and missing pieces. That is why scientists are already looking past the first headlines. The words unexpected finding make it sound like one dramatic surprise, maybe one number on a chart. But the real surprise is more stubborn than that. Webb found a planet whose upper atmosphere is both clearer to see and harder to explain. And the timing matters for another reason. NASA and the planetary science community have been thinking seriously about a future Uranus mission, often called Uranus Orbiter and Probe. A mission like that could watch the atmosphere, magnetic field, rings, and moons up close for years instead of hours. The new Webb results make that kind of mission feel less optional and more necessary. Because right now we are still dealing with a short window. One 15-hour observation is powerful, but Uranus changes over seasons that last decades. If the cooling trend is real and ongoing, scientists need to watch whether it keeps falling, levels off, or reverses. That takes repeated observations, not one visit. The same goes for the auroras. Are those two bright bands always there in the same basic form? Does the dark gap stay fixed, or does it shift with solar conditions, season, or the planet's rotation? A single map can reveal the existence of a pattern, but only more maps can show its life story. So we reach the point where the story changes from discovery to risk. The risk is not danger to Earth tomorrow. The risk is that we keep using simple models on a class of planets that turns out to be far less simple than we thought. And that matters because Uranus is not just Uranus. It is also a stand-in for many giant worlds beyond our solar system. This is where the stakes quietly get huge. Astronomers find many exoplanets that fall into the size range between Earth and Neptune. Ice giant-style worlds may be common in the galaxy, maybe even more common than planets like ours. If we do not understand how one nearby ice giant moves heat and energy, our guesses about distant ones stay weak. So take a second and make your final prediction before the verdict. Is the biggest lesson here about one strange planet, or about how often the universe fools us when we think we have a simple category? Tell me which way you see it in the comments. Here is the verdict. NASA's new map did not reveal a dead frozen world, and it did not reveal a fully solved heating system. It revealed that Uranus's upper atmosphere is strongly shaped by its crooked magnetic field, marked by bright auroras and dark gaps, and still cooling in a way scientists cannot yet fully explain. That is the unexpected finding, not silence but organized mystery. And that verdict brings us back to the opening claim. Yes, Uranus is cooling, and yes, that really does seem to be happening. But no, that does not mean the planet is shutting down. It means the ways heat is added, stored, moved, and lost above Uranus are more complicated than the old picture allowed. In plain words, Uranus is not breaking the laws of physics. It is exposing how incomplete our version of those laws becomes when we try to use them on a tilted ice giant with a warped magnetic field. Webb has turned a blur into a map, and the map says the same place can glow, twist, and cool at once. That is why the result feels so unsettling. There is also something deeply human in this kind of discovery. We looked at Uranus for a long time and thought distance had already explained it. Then better vision arrived, and the planet answered with structure instead of simplicity. That is a reminder that the universe does not become smaller just because our labels become comfortable. And maybe that is why this story lands so hard. It is not only about one remote world with a strange name and a sideways spin. It is about how much can still hide inside a planet we have known about for centuries. A new map did not close the file. It opened a deeper one. If you want to stay ahead of stories like this, subscribe and turn on notifications so you do not miss the next piece. Then tell me in the comments what you think is really driving Uranus's long cooling trend. Seasons, magnetic chaos, hidden waves, or something we have not even named yet. And share this with someone who loves space mysteries, because this planet just proved it is far stranger than its calm face lets on. Thanks for watching, and for thinking it through with me.